recording. Just 1 second. I have my own answer key here to look at. That's how I know what to type in every time. I don't have it memorized. So yes, there we go. All right. So I have to bring that up. Now, once you're in Posit Cloud, you can go to the Files tab over here on this panel, and I'm going to go back. These are the ones with the blanks filled in. I'm going to go to the Worksheets directory and open Part 2 worksheet, and that will bring up the one with the blanks filled in for today. There, we haven't done anything so far. We're just getting started, getting set up, get into your, open up the session on Posit Cloud and open up the worksheet. That's all we've done so far. Okay, so what are we going to do? First of all, since we're starting on a fresh session, we want to load all the packages to make the functions available that we're going to be working with today. And then, by the way, this is a credit to Matt for writing all the code here for this lesson. I did edit it a little bit as well. So highlight everything up to where we're going to import the data. And this, if I run all this, it'll load all the packages and it will define a customized plotting function that Matt created to draw volcano plots later that we're gonna be. So go ahead and hit Control Enter or Command Enter if you're on a Mac, and it will. Yeah, and then if anybody, I'm pretty sure that these packages are all ones that we used yesterday. So there should, if everyone got their stuff installed locally yesterday, we shouldn't have any issues today. But is everybody able to? The folks that are using their own R, are you able to load all those packages? Are you able to? Do you have all those? Okay, and if people on Teams I see are giving thumbs up, so if you're on Teams, you can just give a thumbs up if everything is working for you. That would be nice. Great. Next step is we're going to import the data, and this time the data is kind of in more of the form that I think you would probably obtain it in practice, which is a text file, although it does say imputed, so I think some sort of pre-processing was done on this. I don't know, Matt, if you have any idea what form is this data? This isn't like what comes right off the instrument. There's some processing that's been done. If you can comment on that, I don't know anything about that.
So you can see that the name of the file is Perseus. So this is coming off of like whatever machine this was done on. Basically, this is the software used for the data pre-processing, and basically it's doing like basically it's going in and doing the pre-processing, and it's applying some things like, Q values for like the confidence that this is the protein that we're looking at.
Okay.
And so you'll see some columns that sort of like work as these labels for like, oh, is this a contaminant? Is this the reverse? So these are all things that the software does, called Perseus.
So that's like made by the manufacturer of the instrument or whatever?
Yeah, it's made by MaxQuant. So I think this came off of I think that MaxQuant is the machine by Thermo Fisher. Yes, yeah.
So Thermo Fisher has done some kind of secret sauce to like process the data and give us it in a better form, but we're we're calling that raw data right now, even though it's not totally
Yeah.
raw. It's already been like worked on somehow.
It's transformed in the software.
Yeah.
Like
Yeah.
the transformation. So like this is what you would get from, and there, this has already been filtered too. So you can see, yeah.
That's right. We'll get into that shortly. So yeah, if you're on Posit Cloud, you can run this line 57, which will just, it's not going to import it yet, just defining a text string of the location where the text file is. But if you're on your own RStudio, on your own local computer, you'll want to uncomment line 58 by deleting the comment character and then run line 58, which will just define a URL where the text file is that I posted on a website. Either way, we're going to then proceed to line 60 and then just put your cursor anywhere in there and hit Control Enter. It will import the data from the text file, whether it's local on the demo server or from the website. And you can see if it worked correctly, you'll see that we have a 3000 by 56 table here. Everybody got that? Sweet. So yeah, so there's about 3000 features. Those are the different proteins in the proteome, but 56 columns. If you recall, we only have 18 samples, right? 6 from each of the 3 time points. So what all is in there besides that? Let's take a look at the data and see what we're dealing with. So let's go ahead and use the call names function. That's going to give us the names of the columns in the table, all 56 of them. So we'll hit Control Enter, and then in our console, we'll pop, make that part bigger. Yeah, then in our console, we'll pop up the column names. Okay, so here we have them. You can see we have our like 0 hour time point, sample number 1. So like the first 18 columns are the actual data with the 18 samples, 1 column for each sample for the first 18. But then we have like a bunch of sort of metadata or quality control columns that give us more information about the quality of the ID, I guess, for each protein that we have in the proteome. Yeah, I mean, I can't comment on exactly what these all are, but some of them are like names of the protein and others are flags indicating potential issues with that row in the data. So let's take a look. So yeah, the ones that that Matt identified as being the ones to use to filter out bad rows from the data are the ones reverse, potential contaminant, and only identified by site. Matt, if you could comment on what those mean.
So basically, I don't have like a sort of, basically like these will be like, you're either going to get an empty value in these columns or you're going to get a plus, basically just being like a hit, right? And so generally the kind of the pre-processing software, I think in like Perseus will go and flag like these 3 sort of features. Mm-hmm. And basically you want to go in and remove anything that has this positive flag.
So if everything's good, there'll be no value in those columns. That'll indicate that it's a good protein. Otherwise, it's only has anything if there's a problem.
Yes. So like,
okay.
It's
what does reverse mean exactly? Like it was sequenced in the wrong direction or something?
The reverse flag, because like I had to watch a video about this to understand how to pre-filter this.
Okay.
And they really didn't go into the
they just said
the meat of it. They were like, these are bad.
Out. Okay.
Filter these out.
Whatever it means, it's not good if there's a plus there. All right. So we'll just take their word for it then. And yeah, so the way that the function unique in R will take a vector of values and give you all the unique values that occur in there. So let's use the unique function and then we're gonna we call the data frame data that has the proteome data in it. So data $ reverse means take the reverse column out of the data frame called data and give me all the unique values that's in it. And then we're gonna repeat that for the potential contaminant column and the only identified by site column. And notice that in these ones, you have to put tick marks around the column name, because if column names have spaces in them in R, it messes up the syntax if you don't put those tick marks around it. But if it's just reverse, it's just one word with no spaces, so you don't have to do that. So let's see, is everyone good? We can wait till everyone's caught up here. I see, Xiaoxiu, you have your hand raised. Go ahead.
Yes, I just want to follow up with a quick question about the data itself. Like, I noticed the very last several columns that they have like protein names or gene names, IDs,
Right.
like it is the same as its output from whatever the pipeline runs, right? Like you mentioned, only first few columns are the real data. Is that correct?
So yeah, the first columns are like the actual intensity, or a proxy value for the abundance of that protein, and then the other columns, information about the protein. Each row is a protein, so
It's like metadata for the quality.
that's right. And so I don't know, Matt, do you have any idea how they got the names? They like ran it against a database?
Yeah, they ran it against the database, and then they recommend the majority of the time. You'll see that there's like there's colons, right? Like these are there are multiple names for the same gene, right? Because
that's correct.
So most of the time, people want to take the first name. That's the general consensus. You just go all the way down to like the end, like that first name, and that's usually the one they pick.
I see. So
is that correct? Just to take, or I mean, as an example, I get it. Like to make it easy, but in reality, do we need to figure out which is exactly there, or you can figure it out later?
For the sake of this one, we did not strip the names, so we should have full names of and then you can go back retroactively and kind of look at it and say, oh, this seems like the correct one. Majority of the time, it's going to be the same name.
I see. So yes, I'm just looking at the first few rows of the data. The protein IDs column, first row has like a very, very long text string with protein IDs separated by semicolons. So apparently people just take the first one.
They take the gene ID column.
Okay.
Yeah.
So there's a lot of protein IDs, and then there's somehow they got one name from that, and then several gene IDs, but yeah, so.
Okay.
I'll just take Matt's word that the common practice is to take the first one off of that. But there's uncertainty obviously associated with these calls that they may copy.
Thank you.
No problem. So let's take a look, running line 72, at what are the unique values in the column called reverse in the data. There says NA, which is R's code for a missing value. So that means the entire column reverse is made up of only missing or empty values. There's no plus flags in there at all. So it looks like either the data is perfectly clean to begin with, or it already got filtered, which I would say is probably, in this case, it most likely already got filtered. Any flag rows have already been removed here. But we're just going through the steps of what you would do to remove them, since you probably won't get such clean data in reality. So this is what you would do. And then potential contaminant, let's run that line to look at anything flagged there. Again, we get only missing values. No, nothing is flagged as a potential contaminant and only identified by site. Same thing. Again, it's all clean already, I guess. So, yeah. So now, this is how you would go ahead and, if there were any flag rows, how would you remove them? Let's go ahead and do that. So this is just like this line here, the length parentheses row names parentheses data is just a check for us to see how many rows there are right now in the data frame, and then see how many got removed when we do the filtering. We're not, since there's nothing flagged right now, we're not actually going to remove any, but this would be a good check to do in practice. So this should be 3,321 whenever we run it, because that's how many rows there are in data, as we can see on the right. Pre-contamination. So we'll run that line. As you can see, the value is 3,321. The L is how R identifies integers versus numbers that have decimal points at the end. So yeah, 3321. And now we're going to use, here we're going to fill in the blank. The subset function is a function. We can hit escape to get rid of the autocomplete. Subset is a function that, yeah, it takes a data frame and gives us only a subset of the rows. It removes some based on a condition. So only the rows that meet that condition are kept. Everything else get rid of. So this not, the exclamation point means not, so it negates anything after it. And the column we want to subset by is reverse. Not, reverse, and this percent in percent means any values in the column reverse that match the thing after it. And we'll put here the plus sign with quotes around it, since apparently this Thermo Fisher proprietary software will give plus in that column if it's flagged as a problem. So basically, not, reverse, in, plus means keep only the rows that do not have a plus and get rid of everything that's plus.
So the reverse column, I had to pull up the, so it's marked with a plus when this particular peptide was found part of a protein derived from the reverse part of a decoy database, right? So, and then it says, it prefaces with, these should be removed for further analysis. And so there's like a new, I can send this link to everyone of the,
Okay.
It's basically the description of each, if you're interested in what each column means in the context of the software.
Yeah. So yeah, it's always good to like understand what these different steps are doing. I mean, I didn't quite understand exactly what he just said, but you know, it probably could benefit you to be sure you know what exactly is going on here. Since these are things like they are standard procedures, but really if you were writing a method section for a paper, you should like everything you do should be reproducible so that people can get the same results as you. So it would include everything down to these steps, even if they're like standard, you know, you have to say you did them and exactly what you did. So important to know what it is you're doing. So I'll just go ahead and highlight this whole block here with 3 lines and run it. So we've now subsetted by getting rid of anything with a plus in reverse, potential contaminant, or only identified by site, which we already knew was nothing, but we did it anyways because it's to show you how it would be done. Post-contamination, now we're looking at how many rows are in data now. We'll run that line. And then we just want to print what percent of the rows did we keep from before. 3 divided by post times 100 should be 100%. And it is in fact 100%. So we didn't get rid of anything when we did that. But we're just going through the steps. Any questions so far? Okay, so just to keep you oriented, the next thing we're going to do is now we're gonna just pull out the columns that have the intensity values for the proteins, the actual numbers in the data. we're gonna make a separate, smaller data frame with only 18 columns that just has those numerical values in it. And then we're going to plot their distributions and do any transformations we need to do. And how are we going to pull it out? Well, if you recall back from when we looked at the column names of data, I'll just scroll back up to find that. The columns with the data in them begin with the time point 0H, 4H, and 24H. So you could just say get columns 1 through 18, but that's not the best practice because what if the data come in a different order later? It's better to make an explicit rule for which columns we want so that it will know that that will work, you know, in case somehow the column order gets changed, we will still get the right columns. So we're going to use a regular expression, which means get all columns that match this specific pattern. And regular expressions have their own special syntax, but I won't go into it. But this means any column that starts with either 0H, 4H, or 24H, we will get. And the function called grep, grep, is what is used to test regular expressions, and it will give us a true for every column in data that matches and a false for every one that doesn't. And then value equals true means it'll give us the actual column names that match. So we'll hit Control Enter to run this. You can see intensity calls is 18 elements long and has the names of the columns that we want. Then we're going to create a new, smaller data frame with fewer columns called analysis data by selecting only those columns from the data. And so we're going to use, you see this dplyr : that means keep the 2 colons there, get rid of the periods. We're going to use the function select, but there's multiple packages that we had select in the annotation package that we use to get the mouse gene names, and also it's in this dplyr package, which is used for manipulating data frames. So you can say specifically by putting the name of the package, 2 colons, followed by the name of the function. That just makes sure we're using the right select function. Otherwise, it can cause issues. And then we're going to use the all_of function, meaning to take the data frame called data, select all the columns that are named in the vector intensity calls, and keep only those columns, get rid of the rest. But we'll still have the metadata columns in the original data frame called data because we're making a new one called analysis data, which is just going to have same number of rows as data, but fewer columns. Hit Control Enter when you're in there. So yeah, now you see that analysis data has same number of rows, but less columns than data. We can look at the first few rows of it using the head function. From that line, you can see that we have values in the 20 to 30 range. So remind me, these are pre-transformed already?
Yes, these are pre-transformed. I think that they're pre.
So yeah, probably if you see values that are in this small range like this, it would probably indicate that it's been log transformed already, since raw intensity values would be in much higher. What units are they originally in? If you have any idea?
They get if you read the raw, it's like thousands.
Right.
Yeah. So it's very, very, yeah.
Because it's some measure of like luminescence that's coming off these things.
Yeah. When you look at the off of my head, when I looked at the raw analysis data, it was like, or maybe even millions. Yeah, since it would have been.
Because this is in the log base 2 scale, so 26 would be 2 to the 26 power. It's going to be a huge number.
Yeah, so they're all really huge number. And
like what's 2 to the 26 power, for example, is
right there. Yeah,
you know, 67 million. So yeah, that's a lot. But we got 20 or so. So we know it's log transformed, and we can use the range function, which gives us the min and max in that data frame, and na.rm equals true means ignore missing value. I don't think these data have any missing values, but it's good practice to put that if you don't want missing values to show up in your range. Otherwise, you'll get a missing value for the min and max. We'll hit Control Enter. Yeah, so it goes from about 20 to a little less than 40. And we want to look, even though these data have already been transformed, this is something that we're just doing kind of for teaching purposes. We want to sort of untransform the data by, if you took the log base 2, the way you undo a log base 2 is to take 2 raised to that power, right? So that's what the definition of a logarithm. So we'll take 2 raised to the power of analysis data. You can just like raise an entire matrix to a power and it will just do that operation on every number in the matrix, and then -1, because usually when you did a log transformation, it was log of x plus 1 in case there was any zeros in there.
Which I don't think there were.
Yes,
But I just for the sake of it.
Yep. And then we're going to do a for loop to make a histogram. A for loop loops through and repeats the same code over and over for every value. Every time you go through the loop, it increases usually the value by 1. And so what we're going to do 1 colon, meaning 1 through, and we're going to use n col, meaning the number of columns. So we're going to say, which is 18. So it's going to repeat the same code for every value of I between 1 and 18. And what the code is going to do is draw a histogram. We're going to use the function hist, which is the base R function to draw a histogram. Histogram of raw analysis data brackets I, meaning column I in the raw data. And then main means what is the title of the plot. It's going to be the column name, which is just like, the sample 1 from hour 0 and things like that. So I'll hit Control Enter to run that. And it makes 18 plots. They all show up at once, so you have to kind of scroll through and see them, but they all look about the same. They all are extremely skewed distributions, right? Because this is before the log transformation. We have many, that's typical of data that like this, which, right, intensity cannot be negative, right? The lowest intensity you can have is 0. Most of the proteins are present, not at all, or in very small amounts. And a few samples have extremely high concentrations. That's what you're going to get, a skewed distribution, right? It looks like it would be like the distribution of income or of net worth of people in the United States. You'd have like a bunch of people with very little money, and then Elon Musk would be like at $1 trillion or whatever. So it's very skewed, right? So like that's not a normal, that's not a bell curve, because you can't have less than $0, but you can have up to $1 trillion apparently dollars. So that's what it would look like. But if we took a log transformation, we're gonna log transformation will stretch out the smaller values and crush together the bigger ones and give us something more symmetrical, which helps meet assumptions of the models we're going to do later. So let's undo the transformation we just did. Basically, we're just getting back to what we had before, using the log2 function to take log to the base 2 of the untransformed data, run that, and then run the for loop as well, and make a histogram of each one. You can see, just like we thought, there's lots and lots of histograms there, but they all look about the same, where we have this, I mean, they're not perfect. They're a little bit skewed still. Like this isn't exactly symmetrical. I feel like there's more value, more in the lower half than the upper, but it's much, much close enough for most models that would assume normal distribution. That's pretty close to bell curve, I would say, just by eyeballing it, which is good enough. Because linear models don't have, like, a true perfectly normal distribution does not exist in nature. It's a mathematical equation. No true data set exactly follows a normal distribution. It just has to be close enough to not give biased inference from the model. So those look close enough to me. Like, people are always doing normality tests and things, but I hardly ever do them. I just eyeball the histogram and say, well, that's close enough. Okay, next step is, just as we did yesterday, we're going to remove rows that are all 0 for every sample, right? Because those would not be meaningful. And I think you didn't add anything to like remove low expression proteins, just all 0 ones, right?
Yes, just more or less just to do like a proof of, right, like this is what you would want to do. But like I said, this is already heavily filtered data.
That's right.
They had already.
That's right. Because yesterday in the transcriptome analysis, we removed everything that was all 0, obviously, but we also removed a bunch more that had a few non-zero values, but that were like only a few small values and didn't go above a certain cutoff. We removed those, but we're not doing that here. We're just removing ones that are all 0. And I don't think even there are any to remove, but this is just like, again, what you should do in case you get data in a more unfiltered form that has zeros. And the way you do it is use the function row sums, row capital S for sums. So we say, okay, and then equals 0. So what does this mean? Row sums means take the sum of every row. The double equals mean test whether it is equal to 0. So we're going to test whether each row is equal to 0. And then these brackets is another way to do subsetting. Without the subset function, it means keep only the rows that match that. And the comma with nothing after it means keep only those rows, but keep all the columns. If we have nothing after the comma, it means keep all the columns. So we'll call that filter. And control enter. Then we'll look at n row to look at the number of rows in that. Right, yes, oh yeah, you wanted the ones that are 0. So this is any rows that would be filtered out. 0 rows are going to be filtered out, so we don't have to do the filtering.
I would like to add, I think you're more likely with this kind of data to have just missing values rather than zeros, but you would convert those to zeros.
Okay, so a missing value means no intensity was found. Okay.
Which they, like I said, this is heavily pre-filtered.
That's
so
right.
They already did it. Yeah.
Because in data like this, there's no such thing as a true 0. Like everything is, it's very hard to get a true 0 because there is some background intensity on all the samples. So yeah, but things would get truncated to 0 if it's below a certain threshold, like a limit of detection set by the machine. Okay, so now, where were we? We're going to, I believe we already did this, but once again, we're going to make a new data frame called MAT, as in matrix, by selecting all of the intensity columns. And you can see that if you start typing that, it will bring up autocomplete. You can hit tab to finish the name, run that line. And this S-apply mat, class means look at each column of matrix of mat and see what class it is. Make sure they're all numeric, so we didn't accidentally get any of the text columns in there. Yes, they are all numeric, so that's good. And then we're going to add some gene names to each of the rows. Remember, we saw in the data that there were gene names associated with each row, so we can, to make our analysis more informative later, we can actually see the names of the genes that we're dealing with, the code for these proteins. We can add those as the names of the rows of the matrix. So we're going to make a vector called gene names from the column in the data. So we'll run line 125 to do that. And then we're going to assign that to the row names of the matrix called MAT. And that we'll use the function make.unique because some gene names may be duplicated and that will cause problems with the analysis later on. So if any of them are duplicated, it'll just append an extra value like a 1 or something onto the end of the duplicated ones to make sure that there's no duplicates in the actual row names.
And like yesterday with same thing with the transcriptomics, you can do the same thing and then kind of retroactively look at those duplicated values.
That's right. That's right. Make dot unique. Run that. Now, if you remember that most of the omics and multivariate analysis that we have been working with require an N by P matrix, where each row is a sample and each column is a variable. Right now, we actually have a P by N. We have each row is a variable or a protein, and each column is a sample. So we want to transpose the matrix, turn it 90 degrees to have it now be in an N by P format. The T function in R is what does the transposing. So we're going to say, we're going to make a new matrix called mat underscore T for transpose, T parentheses, and when you open a parentheses in R, it automatically closes before you, T parentheses mat. And once we run that line, it will make, it says large matrix. If you click here, it will give you the dimensions. 18 by 3,321. That's what we want. 18 rows, 3,000 columns. Everyone good? We can take a 5-minute break if people need to go to the bathroom or anything like that, or if need to get called up. Yeah, let's take a 5-minute break and start again at 9:52. What do you say? All right. Good stopping point. So.
The gene names are like annotated after also.
Okay.
So it's not like, I don't think that's on from Perseus. But
I see. So somebody else did that.
Yeah, you go in and you put that.
Okay.
So that wasn't part of the, we already had it annotated.
So that was another, so that would be something that they would have to do in practice or whatever.
I'm pretty sure they do it. So Max Quant and Perseus are web-based, or not
Okay.
web-based,
Oh, I
sorry,
see.
they have UI, so they're like software that you can download.
I see.
So not web-based, but you can do all of the, in Perseus, you can do the differential abundance.
Okay.
The PCA. Yeah.
I never liked doing stuff like that in the manufacturer's software. I don't ever trust it, but it's probably fine. But
I don't think that these are, I'm not quite sure. I couldn't get a clear answer because I'm not familiar with software, but I think they're developed by a lab. Maybe it's not.
so yeah, it's probably legit then,
Yeah.
Yes. But good to do it ourselves though.
Yeah, you get the same results.
Yes. Yeah. Were y'all able to do everything and you caught up? Sweet. That's all. I see you have it. Very good. Just want to make sure it's all good.
I'm following mostly. I took Python.
Okay.
So,
Yeah.
but not R. So
Yeah. It's pretty similar. I mean, yeah, there's like little weird things.
we were like 4 loops. I was like, yes.
Yeah, but Python starts at 0, not 1.
Yeah, it's annoying.
R starts at 1 and Python starts at 0, so that's kind of hard to like, it's easy to switch between them. But
If they had more libraries or stuff like this, I'd do everything in Python. If it's more simple.
Yes.
But
I thought it's, I don't know, simple for me. I don't know.
I find it to be like, they're both pretty intuitive,
yeah, I mean, yeah, they really mostly do the same stuff. I mean, yeah,
I know one unit.
yeah. Python, like, in the past, it was like, okay, machine learning is like better for Python because it has more libraries, but now you can do it all, you can really do the same stuff in R. I don't know. But what about Julia though? I mean, now everyone should just switch to that. It's like,
Yeah, it's
my friend is always trying to get me to switch to Julia,
for
but
the plotting and stuff I've seen.
Yeah. it's like, so to be much faster,
Or
but
like, yeah, or like if we could just, I'm not gonna learn Rust,
yeah,
pretty good. Like, but I've seen a lot of people use Julia for like metagenomics. and
Yeah,
stuff.
yeah. Because like in R and Python, you want to do something really fast, you like write C++ code and then like integrate that in. But in Julia, you don't have to do that because it like everything is compiled and it's just as fast as C++, but you write the code, it's like it was Python. Yeah, but I still haven't bothered to, I tried to learn it once and then gave up. Because there's just not as many packages and stuff, like,
Yeah.
yeah, that's the problem.
Maybe eventually.
Yeah, someday.
But do, I have like a general statistics question.
Okay.
So you don't like ever do like Shapiro-Wilkes or anything, you just.
I mean-
What?
Not usually, no. Yeah, that is right, because those tests are too sensitive, and if you have a big enough sample size, you get a significant deviation from normality, even if the data is like almost perfectly normal. So, I did, yeah, I mean, sometimes I do some residual diagnostics and things, but mostly I just do it by looking at the residual plots and not, yeah, that's another thing. People always do the normality test on the data, but really it's the residuals of the stat model that have to be normally distributed, not the data. So that is one thing to keep in mind.
Because you can technically, you back transform it and put plotting and things like that, right? It's like,
Yeah, so, yeah, this, yeah, I don't really use those tests very much.
where you can back transform it to like something non-transform and then plot that way, but have the statistics for.
That's right. Yeah, after you run them, especially if you do a GLM, you can transform back and yeah, that's right.
I've been trying to get Peter, I think you should watch the GLM videos and the workshops. I like,
Yeah.
I've been using them for
I have
learning how.
some lessons on that stuff too, so. All right, I think we've had 5 minutes now, so hopefully everyone's good and we can keep going. So let's see, where were we? Yeah, so it says we're gonna standardize the data, and by standardize, I mean Z transform, which means for every, let's see, now we have a column for every now our columns are the proteins. So we want to, some proteins are just more abundant than others baseline anyway, but we're not really concerned with that. We just want to know the relative differences within each protein. Are they changing by time point? So we want to standardize within each protein, meaning subtract the mean and divide by the standard deviation so that every column has a mean of 0 and a standard deviation of 1, so that we can compare two proteins, even if one is just naturally more abundant than another. We're just going to standardize. So there is a built-in function in R to do that, which will do the Z transformation or the standardization on each column, which is called scale. Scale parentheses, and then we're going to use the mat underscore T, the transpose matrix, and we're going to create a new matrix called mat T scaled, which is that standardized one. And yeah, and that's especially important when you're doing multivariate analysis, such as PCA, to scale the columns. So now you can see that, mat T has values going around 26 like we had before, and mat T scaled is going to have values that are, 1.3, -1, and things like that. So it's everything has a mean of 0 and standard deviation of 1. Then we're going to do a PCA like we talked about yesterday. It's a very, very simple multivariate analysis that's just going to quickly pull out patterns in the data, finding the lower dimensions in the data that explains the most information in that high dimensional data. So instead of having 3,000 dimensions, we're going to bring it down to 2 that explain the most variation and see what it looks like. And so PR comp for principal components is the R function that does a PCA. We're going to run the PCA on the scaled matrix. And then this, we're going to look at the variance explained by each PCA axis. And ideally, PCA axes are always arranged in descending order of how much variation they explain. And it would optimally, you would have most of the variation be explained by the first few axes. So we'll take the PCA $SDev. So that's the standard deviation column within the PCA output we created. And we're going to square that because the variance is the square of the standard deviation. And then we're going to divide it by the sum. So for each column, what proportion of its variance relative to the total variance. We'll get a value between 0 and 1 for each column. And they'll all put together add up to 1. Control Enter to run it. It's called var x. So you can see over on the right, the first column, the first axis explains 25.9% of the variance. The next one, a little under 21%. So even though we have 3,000 columns, we have been able to find two axes that put together explain almost half the variance, like 26 plus 21, almost half. And then we're going to calculate that rounded to the nearest percent so that we can label our plot. So round variation underscore explained bracket 1, that means take the first value from variation explained, right? It's not Python. If Python, it would be 0, but this 1 is the first value, and times 100, and round to the nearest whole number. We'll do that for both of them. Run those two lines, and then we're going to create a data frame with this information so that we can plot it. And I won't get into too much of the syntax, but we want a column that says what are the names of the samples. Use this syntax to clean up the names a bit for plotting purposes. Not super important to know exactly how that's done, but within the PCA object that we created, there's an object called X, which is a matrix of the values of the scores for each of the 18 samples on the first two PCA axes. PCA $X bracket :1 means take the first column from that matrix and call it PC1 in our output data frame, and do the same for column 2. Run that. And now we're going to make a plot. This is a PCA plot. Now there are like sort of default functions to do PCA plot, but we built one ourselves because it's always better to build it yourself, and with the ggplot. And not to get into too much of ggplot, but basically the way ggplot works is in the first line of the ggplot, you tell it which column from your data, PCA-DF, goes to which aspect of the plot. And the first argument there is going to be whatever we want to be on the x-axis, which is PC1. The next argument is PC2. Label means what are we going to, we're going to put little text labels around our scatter plot, and we're going to label them by the name of each sample, each of the 18. So there's going to be 18 points on this scatter plot. And we want to color it by group so that each time point has a different color. We can see, just like we did yesterday, if the ones from the same time point are clustered together, indicating they have similar proteomes, more or less, if they come from the same time point. And then there's various code to like label the points and things like that, and color them. So there we go. I'll zoom that in somewhat. So yeah, so you can see that the clustering is pretty decent. Every time point is every sample is closer to the ones from its own time point than it is to anything from another time point. And in our PC1 axis, which explains 25% of the variation, is kind of separating time point 4 from the other two time points. 0 and 24 have low values on that axis, and 4 has high. And then our PCA2 axis is pulling apart the 0 from the 24, more or less. So there's kind of like, seems like time point 4 is different in its own way, in a way that's more different than anything else, because it has the most variation associated with it. And then still a pretty decent amount is between 0 and 24. Everybody got that? So this is just a quick visualization to make sure there's nothing weird going on with the data, and the time points sort of seem to make sense. Again, this is like I said yesterday, these are very strong patterns because we have, these cells were directly manipulated in a way that's like bound to influence the proteome quite a bit, where like if you're doing a nutrition study, it's not going to have, you're not like putting chemicals directly on people's cells, so it's not going to affect the proteome quite as strongly. So this is like a bigger difference than you might see in other contexts. Okay, so yeah, now what remains is for us to do the differential expression analysis, or differential abundance, I guess. I guess you can still call it expression because it's proteins, just like we did yesterday for the transcriptome. And that's kind of what the rest of this lesson 2 is all about. And it's very similar, if not identical, to what we did yesterday. So basically we have to create that design matrix. Yeah, Peter.
Oh, so just to clarify here,
Yes.
the design context matrix, that's not on the standardized.
The design matrix is not the data. That is part of a linear model, includes a design matrix, which is basically a mapping of which group each data point belongs to. So it only is going to contain zeros and ones. So it's going to be, we have 3 time points, right? We have 18 samples. So it's going to be an 18 by 3 matrix. And each row is going to have 2 zeros and a 1 in it, indicating which group each sample comes from. And then the contrast matrix is going to tell us which pairwise differences we're going to take. So this is independent of the data, right? So call names Matt. If we could have put if we could have got that information from our scale data, but we're not actually using the data. We're only using the names of the samples. So it doesn't matter where we get it from. So we're going to create a object or a vector samples. Run that line. Yeah. So it's just the labels. 0h underscore 1 is just the labels, not the data. Then we're going to basically use a regular expression to get rid of the underscore number part from each one. So they'll just be 0h, 0h, 4h, 4h, and so forth. To get the groups for each sample, run that line. And this, you could do this in a more manual way, I guess, but this is probably the best practice way to do it. So here are the groups. This is the text with which group each belongs to, and then we're going to convert that to a factor because we want them to be in the right order, 0, 4, 24. So this just confirms that the factor levels are ordered the way we want them to be. Run that. Now we're going to use the model matrix function. I think this is pretty much exactly as we did it yesterday. Here's the formula for the model matrix. Tilde means by, 0 means we don't want to have an intercept in our model, just the 3 groups. 0 plus groups. Yeah, so 0 means no intercept model. We just want a column for each of the 3 groups. And that makes it easier for us to do the contrast later on. Control Enter. So yeah, design is a model matrix. You can see it's only got zeros and ones in it. We're going to make column names so that we can know, just to make it easier to label our graphs and comparisons later. Now let's look at the design matrix. You can see it, right, it's just zeros and ones. It just indicates that sample 1 comes from time point 0, samples 7 through 12 come from time point 4, and so forth. That's all it is. And then we're going to make a contrast matrix to say we want the difference between these 1 and 2, we want the difference between 1 and 3, and we want the difference between 2 and 3. Those are going to be our like statistical tests we're doing. You could do different ones if like you wanted to compare a bunch of treatments to a control, or if you wanted to do interactions, you'd have to make a more complicated contrast matrix. But for now, we're just doing a one-way ANOVA kind of thing, comparing 3 means. So it's a simple one. Make contrasts is the function. And so yeah, we're taking the pairwise difference, we're subtracting one mean from another for each of the pairs. H0 minus H4, and we're giving each of those contrast names just to make it easier to see in the output what each one is. hit Control Enter. Say our contrast matrix is a 1x3 matrix. If we just type the name contrast matrix in the console, you can see it's just a 3x3. The first contrast is take time point 0, subtract time point 4. We want to take time point 0, subtract time point 4, take 4. Yeah, so now we're going to do our differential abundance analysis to look at whether any of these proteins differ significantly in how much there is of them at different time points based on our sample of 18 cells or 18 proteomes. And we're going to use the LM capital F fit function. This is exactly what we did yesterday. And so we're using the unscaled one because it does its own internal scaling inside of this function. So we can just pass it it's not completely raw because we've already taken the log base 2 transformation on it, but we don't have to do the standardization. And design is the design matrix saying which time point each sample comes from, which we need to be able to compare them. So we'll run that to fit the linear model. Then we're going to take our contrasts to look at the difference between each pair of means. Contrasts.fit. The first argument is the fitted model object and contrast underscore matrix. So what this is doing is it's going through each of the 3,000 and whatever proteins and comparing each pair of means between each of the time points for each one. And seeing if there's a significant difference in protein abundance between them. And then we're going to use the empirical Bayes method to shrink those values so that we're basically correcting for the multiple tests. And since if we just did it by fitting 3,000 linear models independently, we would get a lot more significant results than maybe is warranted, because you can get significant results by chance if you do enough tests, just even if the data was random noise. So we're calling that fit 2, and then we're going to take the empirical Bayes correction on that. Oh yeah, and I know yesterday we made the those like mean variance plots for it. We can do that again here just to see what it looks like. The plot SA, that's not in the code here, but I'm just adding it down here. So yeah, it's like, well,
Not perfect.
it's not perfect because there's like, we should see kind of no pattern in this at all, but there is, I mean, like the line's flat, but there's like clearly something going on there. But yeah, I don't know. It's not perfect, but at least the line is flat. So yeah. So that's something we can work with. Now the remaining code here is simply just working. That was all the like sort of modeling was done. The rest of what we're going to do is just pull out results and make plots. Like we're going to make volcano plots, Venn diagrams, and upset plot of the results, which are things you might put in a manuscript or a presentation based on this. The plots we're making are not like super nice publication quality. They're kind of just like for us to look at them. But you know, if you wanted to put them in a manuscript, you'd probably work them up a little bit more than we're doing now, but we just want to look. So we're going to use the top table to extract the differential abundance results for each of the pairwise comparisons between the time points. And it'll give us the p-values and things like that after the empirical Bayes correction, because we're going to use fit 2. That's the empirical Bayes corrected contrasts. And which contrast do we want? That we called it H0 underscore versus underscore H4. And then number equals infinity means we're going to just get all of them, not just the top however many. So we're going to do that 3 times, once for each of the pairwise. contrast we did. So we'll run that, boom, 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 for each of those. And then we'll add a column with the gene name so that we can plot the actual gene names on the volcano plot. So if you know, any of these genes are relevant to you, you can see them on the plot and see which ones are the ones that have the biggest difference. So then we'll run those 3 lines to do that. Yeah, we'll run line 190, control enter. Okay, and then we're going to create a volcano plot, and this function is one that is not in a package. This is one, if you remember, we defined this function in our environment a few minutes ago when we started this. But there are also built-in functions to make volcano plots in some packages. So we're going to use this function we created ourselves called volcano. It's called volcano plot because like the dots spread out like an erupting volcano, which you'll see in a second. And we're gonna do one for each of the 3 pairwise. So the differential abundance results we got for times 0 versus 4, we saved in an object called res for results underscore, and I'll go down and autocomplete H0 versus H4. And this second argument is just the title of the plot in quotes. 0 times 0 versus time 4. Let's run that. And we'll take a look and you can see what this volcano plot looks like. So basically the x-axis is the magnitude of the difference in log 2 units. So a log 2 difference of 0 means it's the same at time point 0 and time point 4. A log 2 of 1 would mean it's twice as abundant at time 0 versus time 4. A log 2 of -1 means it's twice as abundant at time 4 versus time 0. And then, -2 would be 4 times as much, and +2 is also 4 times as much because it's log base 2. And then this is the negative log 10 p-value. So the higher that number, the more significant the p-value, because the bigger the difference, usually the more significant the p-value. So the ones that are really meaningful are the ones that both have a large difference and a high negative log p-value, meaning those are the ones that have a big difference and there's not as much variance, like we're very certain that that difference is big. So yeah, I mean, apparently these 2 proteins are 4 times more abundant at time point 4 than time point 0, and we're very sure that that's and so did you apply these cutoffs that you just came up with to put these lines on the plot?
So if you go and look at the manuscript in the supplementary material, this is where they put their volcano plots to this date. You can see I picked the cutoff to try to see if I could sort of match their results.
Okay.
So this was actually the cutoffs that were used in the paper, and you can see the cutoffs in the function.
Okay.
And I think you might be able to, let me double check if I wrote that you can pass the cutoffs in the volcano plot. Like,
So yeah, like you can see that there's this 2 negative log 10, 2, that means 10 to the -2 power is 0.01. So apparently they thought that an adjusted p-value of 0.01 was significant. Other cutoffs could be used in other contexts, and also that they also put these dotted lines at plus and minus, like I think it's like
it's a
0.7 or something,
0.75
because that's like
a 1.5.
a little less than twice as much difference, and so that's where they thought that was meaningful. But like that's not some rule that you have to use that number. They just thought, based on their scientific experience, that was like a meaningfully large difference in expression of the protein. So yeah, I don't know if that's like a number that you would use in your systems, but that's what they wanted to use. Yeah, just to point out, those lines are not like a law, that you can put them anywhere on the plot, basically, depending on your question. So that's a volcano plot, and we can also make a similar volcano plot for the 0 versus 24 time point and the 4 versus 24. Let's just take a look at those. But yeah, they're quite similar you know, in how they look. But the axis goes out even more, I think, on the 0 versus 24, because the difference have a bigger magnitude. And it automatically labels the ones that are above the thresholds. And like, you can see that it's kind of neat that the package GG repel is actually being used to label these points, which will, if you have points that you're labeling with text, it will automatically like detect whether the text would overlap if the 2 points are too close to each other, and it'll draw little arrows connecting the points for the ones that are, you know, so that none of them that minimizes the amount of overlap of the text and dots on your plot, which is kind of nice. And then we can make that also for 4 versus 24. Yeah, so let's also make Venn diagrams as we did yesterday. This will show like, are there genes that are both differential, or proteins that are both differentially abundant between 0 and 4, and also differentially abundant between 0 and 24? Like, how many proteins have like a more sustained difference in abundance over time? Those might be ones that are really important for whatever these long-term, at least over 24-hour processes are going on inside the cell after the fat breaks down. And again, these are the thresholds for adjusted p-value and for log fold change that are considered biologically / statistically significant in this case. They're not necessarily the ones that you should always use, and you can also change them to see what the effect is. But we're going to say adjusted p threshold gets, so that's the left pointing arrow. We're going to assign a value to that name. 0.01, that was the same one that we used in the volcano plot. And the log fold change threshold is 0.5. Yeah, so I think that's the one that's on the volcano plot too. Yes.
What does that translate to?
So 2 to the 0.5 is the square root of 2, which is like 1.4. So it's like an increase in abundance of 40%, basically, ish. Yeah, it's kind of arbitrary. It's just what they decided was meaningful.
And to be fair, you know, in the multiomics, none of this is, you know, there are no p-value cutoffs. There are no log fold changes and p-value cutoffs. So like, even if you go look at the paper, they're not.
Right. So yeah, they just like kind of pulled this number out of their behinds, basically. Yeah, I would say.
I mean, I think generally speaking, like, it depends. Like, I think with transcriptomics, you know, it's the gold standard, I think, would be a log fold change of 2, or log 2 fold change of 2, and then your p-value cutoff would be 0.01. I think generally speaking, that's like what you commonly see, and that's like it's the most confident, I think. But then you can see the different.
But you could kind of justify any number if you wanted to, you know? Yeah. So yeah, that's what they put. You could play with changing the number and see if it changes the Venn diagrams and stuff, but I mean, it will change them, but yeah. So we'll run these 2 lines to set our thresholds. Then we defined our own little function to pull out genes that have a fold change above that threshold and a p-value below the threshold. Log fold change is greater than threshold and p-value is less than threshold. It'll get only those ones. So a gene has to meet both those criteria to be put in our Venn diagram as being different. And then we're going to run that function on each of the 3 pairwise differential abundance results we got. Get _up _genes. That's the name of the function we just made. And we're going to apply it to the result object for H0 versus H4. I'll autocomplete that. Yeah, so we're going to run that 3 times, once for each of the pairwise. I'll hit Control Enter to run that whole block of code there. Now this, I will not go into how this is done, but this basically gives us a 1 if a particular protein does meet the threshold and a 0 if it doesn't, and makes it into a matrix that we can use to pass into our Venn diagrams and upset plots. That's what this does. So I won't explain exactly how that's done, but I'll just run the code. And then we'll make column names for that. Okay. And then next step is to make a Venn diagram of it using the function Venn diagram from the lemma package. Autocomplete that, and we're going to pass that matrix to it. And we're going to use some custom colors that we created earlier so that all our plots have the same color scheme. Up_mat. That's what we're going to use. So this will show a 3-circle Venn diagram because we're giving it a 3-column matrix. So yes, what does it show? It's like, well, there's about 3,000 or 2,800 of the 3,300 proteins did not change in their abundance across any of the time points. Some of them were different between 0 and 4, but not between 24. And, some were different between 0 and 4 and between 0 and 24, but not between 4 and 24. And then there's four proteins that were like different between each of the 3. So maybe they like increased in expression or decreased in expression steadily over time. There's 4 proteins that meet that criteria. So we want to know what are the names of the genes that code for those proteins. We can use the reduce by intersect, which means this is going to give us the names of those 4 proteins in the middle of the Venn diagram. It'll intersect, say which genes are found in both these, in which genes are found in all 3 of these differential abundance lists, basically. So we're going to run that. And then we'll just print the names of the 4 genes by just typing the name of that vector into our console, basically. And so, yeah, these are the 4 genes. I don't know what they are, but if you study mouse brown fat cells, they may mean something to you. Yeah, so now the remaining thing is, I won't go through the code, but just to show you, instead of a Venn diagram, you might also want to make an upset plot, since it's a little better to show complex differences. So we'll just run these lines to make the upset plot, in case you're interested. So yeah, these are the it shows you there's only very few. Those are the 4 proteins that were different between all 3 of the time points, and then there's some that are only different between one pair of time points and so forth. Yeah, that's the end of lesson 2. Does anybody have any questions or comments before we take a break? Awesome. So why don't we come back at 10:35 and do the last and probably most exciting lesson about Diablo. 10:35. I'll just stop the recording so that I can start a new one. So we'll have a separate one for each lesson.
Also,